Hi everyone, welcome back. We'll continue with chapter 6, and chapter 6 is going to actually talk about momentum and reaction wheel. Chapter 5, we have seen magnetotorcus control, and we have also concluded that although we can do a single magnetotorcus control, maybe using V dot, etc., but we can also actually opt for a 3-axis magnetic torcus control, and we have seen that well, the accuracy might not be actually very desirable if you want to do especially a very well specific missions like Earth observation, where you need maybe about 0.2 at least 0.2 degrees of pointing accuracy, etc. So it's very difficult for us to achieve with just only a magnetotorcus or magnetic torque. So therefore, there is another actuator which we have also discussed in one of the first chapter that actually we had. The list of actuators is momentum or even the reaction wheel. So we will see what this device is and how this device can help us to control the satellite. Okay, go on. All right. If you look at rotational, so this is basically a rotational stabilization. Why? Because you have wheel. The wheel need to rotate. So when the wheel need to rotate, wheel will produce the angular velocity. When the angular velocity changes, we can have torque. Okay, when we have torque, we should be able to control the actual attitude of the satellite. If you can remember clearly, magnetotorcus, it doesn't rotate, but it just when we on the magnetotorcus, it becomes a electromagnet. And this electromagnet is going to act with the actual magnetic field of planet Earth. Then we produce torque. So there is no rotation at all. But when you talk about the rotational stabilization type, you must have wheels. So wheels can come in a different form. The first one, let's say how we can come. We can do this. The rotational. This is the first type is actually spin. Now, in order for us to spin, there is how you can spin this. The spin type of stabilization, if you can remember, VSAT 1 uses this type of actual stabilization. The whole spacecraft is going to rotate. Okay, so you can imagine the whole body of the spacecraft is going to rotate, and the antenna have to keep pointing to planet Earth. You can't be rotating everything, then the antenna would not be actually pointing also to the space, to the Earth. So if I'm looking at you, my antenna has to look at you, but my body keeps on rotating. And this gives me a stabilization. Why? If you know that actually when we were small, we used to play top spinning. So you throw that and spins. So when actually when you spin so fast, the whole body is very rigid. If you start disturbing it, it may wobble, but then it will stabilize back because of that actual rotation speed. So the exact rotational stabilization, the first one of those first mode of rotational stabilization is actually through the spin stabilized types of satellite. And more often than not, the spin stabilized satellite will be always cylinder in volume. You won't have a cubical satellite which is spinning. No, you will have a cylindrical satellite because the spin will be constant. Yeah. So please understand that. So why exactly satellite designers have found that alright, it's so boring to only have spinning satellites. You know, the cylinder is spinning. By the end of the day, I have to take care of this pointing. So why not? I make something spinning inside, produce the exact angular momentum. When we play top spinning, when we throw top spinning, let's say you spin very fast. What exactly happens? It has an angular momentum. What is angular momentum? Inertia times by the actual angular speed or angular rotation. Then you have that angular momentum. So when you have a high amount of angular momentum, it exactly gives you the gyroscopic stiffness. That means it's very stiff. Okay, and when the satellite is very stiff, you have external disturbance coming and disturbing the satellite. It would not be disturbed in that sense. So the totally spinning the body might not be really well, I would say, not clever, but Reason being, you got to be taking care of your antenna, etc. Why not I install a spinning body inside and then let the spinning body rotate fast and produce the same amount of angular momentum. Okay? Now, two ways you can produce angular momentum. One, you have a very high speed, so you have a smaller mass. Another way, very low speed, bigger mass. Spin satellite, it's lower speed, bigger mass. You will have quite a reasonable angular momentum. Another way we do it, we stop spinning the body, install something called a wheel inside here, ask the wheel or command the wheel to spin very fast, but to compensate for the exact small, I would say, inertia that the wheel has. So it has to actually spin faster. So when it spins faster, it can produce a similar or even more amount of actual momentum that you need, angular momentum. So the passive stabilization can work. It can also produce the gyroscopic stiffness here. So this is the bias momentum type 2. So now I already start talking about the wheel. Now the same wheel, what I do, I put in 3 axes: roll, yaw, and pitch. Or rather, roll, pitch, and yaw. When I have the wheels spinning in all 3 axes, I should be able to actually produce torque. I should be able to produce torque, then I should be able to control the attitude. That means to nullify all the disturbance, the one that you have calculated in chapter 4. All those disturbances that you have calculated, we can actually counteract that. Okay? Another wheel type is control moment gyro. Now, if you assume that I have, now this is fixed, reaction wheel is fixed. That means fixed at roll, fixed at Y, yaw, and pitch. Control moment gyro. Let's say I have a wheel spinning, but I don't install this wheel in roll. I don't install this wheel in yaw. I don't install this wheel, or may I just install this wheel, let's say, in pitch. But if I can tilt the axis of rotation, I should be able to induce torque in roll, in yaw, for example, depending where I'm going to install. So control moment gyro does that. Control moment gyro says that, okay, good, I have one fixed rotational direction and axis, but when I need torque in other axis, what I do, I tilt the wheel. So when I tilt the wheel, the torque vector will change, okay, and the torque vector is going to also change in a different direction, okay. So that will give me a torque not only in the on the rotational axis, but the spinning rotational axis, but I change the spinning rotational axis, I tilt it, it will give me a torque in a new axis. I keep on changing it, what will happen? I can induce torque. So this control moment gyro, in huge satellites you can find this, in a maybe telecommunication satellite you can find this, but in smaller satellites very difficult to find it, because it comes with a very huge cost. In fact, it's a huge device. In fact, just to highlight, space station has control moment gyro in them. So can you imagine, to control a space station, how big is basically this control moment gyro? It's huge. Okay, so these are the typical ones to use. Now attention, all those satellites, very precise pointing satellites, expensive as well. You will see that more often than not, it will come with a 3-axis pointing. Using reaction wheel will be one of those actually most common option. You want to have an Earth observation mission. Let's say you have calculated all those Earth observation exercises. All those Earth observation satellites, more often than not, will be flying with the reaction wheel, because reaction wheel will give you a good attitude performance, just like what we have seen before. Now that's one thing. Second thing, please do understand, when you have already put the wheel inside the rigid body, the outside volume can be different. That is the reason the newer satellite in 1960s, 1970s, you see most of the satellites are cylindric. But now you have seen most of the satellites are basically more than often is cubical. So it's for us, you can imagine that wheels are inside, outside we should be able to have a cubical satellite. That's why the design, commonly if you look at it now, more and more satellites are basically cubical type satellites. Okay, this is to give you a good example. Now let's say I have a reaction wheel. Let's say I have 3 reaction wheels. I have a thrusters. By looking at this combination, I know this satellite should be able to do altitude control, because I have the wheels, 3 wheels in roll, yaw and pitch, and I know for the fact it should be able to do a orbit control because it has a thrusters, rotational motion, translational motion. It should be doing both, which means that this life of the satellite can be long, can be 5 years, can be 10 years, can be even 20 years when you have this system. But assume you don't have a thrusters, you only have a reaction wheel. You'll be lucky if the satellites lasts for about 3 years or even 4 years if it is a low Earth orbit satellite. Okay? Fine. Okay, now this is just the explanation, nutation. Now nutation happens. For why nutation happens? More often than not, you see, when after you the satellite has been injected into the orbit, it is supposed to actually take some time before it can stabilize. So there are, especially for a cylindric, long cylindric satellites, technically it may nutate. It will mutate because of the actual imbalance it has. Okay, which is partly because of the gravity gradient also. But when it actually do a nutation, one single axis, it does this. Okay, single axis here. Okay, this single axis. Then you start rotating this. That's nutation. So origin is still the same, but you start rotating it. Okay? Technically, nutation happens not always. It will happen more often than not just after you inject the satellite into the orbit by the launcher. You'll start actually tumbling. Okay, so nutation, the tumbling mode. That's why we have, if you learn the satellite technology, we have mentioned also tumbling mode. Tumbling mode is a satellite tumbles. Tumbles can actually also incorporate the nutation motion. Now, this can be actually counter react. Go on. How we do this? Now, remember, nutation is a typical problem in a huge satellite. How we can damp this? We use a passive nutation damper. We don't do it with well, you can also do with the prop thrusters, but more often than not, if you look at in a bigger satellites, you have already a passive dampers. You don't use fuel, you don't use electricity. This damper is nothing but basically it's along like a rod. All those energy from the satellite body will be transferred when you rotate. It will be transferred to the actual damper. It dampens it. That means the kinetic energy will be transferred to here. So you will reduce the damping. So when you reduce the damping, then actually what you do, you can actually start doing the altitude control. Okay, If you have so much of nutation, you can't be actually doing attitude control. You'll be haywire. Go on. All right. Sometimes in a longer body, you have two coupled motion. You have that nutation, which is going like that, okay, but origins from that one axis, goes like this. But not only that, it does a small precession, okay, small precession. This happens quite predominant to a good cylinder. For example, even the launcher, yeah, it may happen, yeah, this will happen. Then there is a small precession. So these are the types that actually you can have. But if you have a cubical satellite, chances are quite low. You may be you might get away with only nutation, then it can stabilize. Nutation, then it can stabilize. All right, momentum wheel and direction wheel. We're going to talk about this. You can Google this up. Well, one of those I think important suppliers of reaction wheels or momentum wheels, Talbix. This is from Talbix. It is quite a robust and height-proven wheels that you have. There are a few other brands as well. So this, whatever you see here, is Talbix because they have a list of wheels that they have. So typical one, you can see it's about 7 kilos, quite a huge one. Okay, so you can imagine, and the rotation basically RPM about 2000. So can you imagine 2000 rotation per minute, 7 kilos, almost, you know. So it produces a good amount of angular momentum. Go on. Again, please understand what is a wheel. The momentum wheel is nothing but it's a disc. It's a disc, and you have a motor and rotor design inside. It is technically a motor with a huge amount of rotor. That's it. That's momentum wheel. It's a wheel. It's a wheel, motor, rotor. Right, go on. So let us actually go back to the actual fundamental. What exactly happens when I have a wheel? So let's talk about the wheel model. The wheel angular momentum. The angular momentum of any wheel, J, is basically the inertia of the wheel and the angular velocity of that wheel. Angular velocity. Then you should be having your angular momentum done. Sometimes some books write this as L, angular momentum L. I mark it as a H. That's the same. Don't worry. Then angular momentum law says that when I change this angular momentum, I should have a torque. It gives me torque. How to change this angular momentum? I should be changing the velocity of the wheel. So if I keep on accelerating, I should have torque. More and more speed of the wheel is going to produce the more torque. But if I have a constant speed, I would not have any torque. Okay. Motor torque is TW, which is this. This is the as I've said, is a purely a motor, rotor, and stator as a design. Okay, go on. Okay, how it goes is this. This is basically a motor control. How normally you do. Typical, basically, first order. Okay, just a proportional controller. You have current, and this is basically the motor constant that you have. So how much a current? This is typical motor controller. Just to tell you. Then how much a current that you inject? That is the amount of actually torque will be generated. Then you have some sort of losses of the wheel. Okay. Then you have eddy current loss, all those, so quite typical. Then it goes back to the actual wheel. Then you have the angular momentum. This is actually the S is a Laplace operator S. So 1 over the wheel inertia would give you the actual angular velocity of the wheel. Typical. Go on. All right. Angular momentum wheel, reaction wheel. Let us see what is these two wheels differences. But again, this is a rotational stabilization. Momentum wheel is going to rotate at a constant speed. It gives out the momentum. Constant speed gives out you the momentum. That means the angular momentum don't change. When angular momentum don't change, you don't have a torque, period. Now, when you want to have a torque, what you have to do is you have to change the angular momentum. So you have already a constant bias, that means a bias momentum you have. That means a constant momentum you already have because you have already speed. If you want to change, or if you want to speed up or break the wheel, you will have that torque. That means momentum wheel can be just constant, can be constant plus can also give you torque. So it depends what you want. You want both, you can have both with momentum wheel. Reaction wheel, you can't have both. You can't have angular momentum. You can't have a bias momentum. Why? Normally the reaction wheels are smaller compared to momentum wheels. So therefore, you don't have much basically inertia to produce the exact bias momentum. Okay. So what it does, if you need torque, that means this is a zero velocity. You need torque, then you speed up the wheel. You break the wheel, you have a torque on the other side. Torque, positive torque, negative torque, positive torque, negative torque, and so on. This is your reaction wheel. Okay. It's dynamic. It's always moving to produce torque. Remember, in chapter 4, we have seen your model of your disturbance is basically sinusoidal. So it goes up, positive down, positive up, positive down, positive up and down, positive down, up, down. So therefore, look at this. Remember that sinusoidal. So it follows your actual torque pattern. That means external disturbance pattern follows. Right. Same goes for this. Right. Good. Again, just a quick one. This is a slightly more. Nominal speed is about 4,600. You see, a typical reaction wheels or even momentum wheel, 5,000 RPM is very common. Quite fast, very, very fast. Very, very fast. 5,000 RPM. Quite typical. You can Google up Talbix, then you will have a lot of details on it. But typically, I just want to give you some sort of overview of what kind of a system. Now, the time constant, if you look at it, it's very fast, about 100 milliseconds. Very, very, very fast. That means I want torque, let's say a 0.5 Newton. I want now. So I can have it within 100 milliseconds. That means not even a second, I'm already done. It's very fast, very, very fast. So it's very quick. Okay, go on. Alright, let us actually look at the single axis control. Now, assuming what this is telling you, assuming I have a wheel, I have a platform, JP is the platform, which is the satellite, and I have a wheel. So let me write the actual equation of total angular momentum equation so that you will know how to actually we can do this. So now total angular momentum equation, I have two rigid body there, the platform and the wheel. Okay. Now don't forget the platform, the wheel is also mounted to the platform, which means that if the platform is rotating at omega p, the platform is also rotating, the wheel also is rotating at omega p. But the wheel itself is rotating at j omega, that means jw, that means the wheels are omega wheel, that means. Okay. So there is two speeds here, two rotational motion here. The platform is rotating, the wheel is rotating. Platform is rotating, wheel is rotating, and because of the platform rotating, the wheel also will rotate because of the platform. So therefore, the important total momentum involved in this system is platform rotating, platform's angular momentum, wheel's angular momentum, but because of the platform's angular speed, angular rotation, plus the actual rotation of the wheel itself. This will be your total angular momentum. Now, total angular momentum, I can rewrite this. The wheel and the platform, I can take it as satellite. I can take this as satellite. The wheel and the platform, I can take this as satellite. So wheel plus platform plus wheel, and is rotating at the speed of the satellite, omega platform, omega satellite is one quantity, means that this is satellite, and the wheel itself is rotating at its own speed. Okay, so you have two components. So this is exactly the same what I've written here. So the actual inertia of the satellite is including of the wheel inertia. We're done. So I can rewrite it easily. The inertia of the satellite, total inertia of the satellite, is inclusive of the wheel times by the actual angular velocity of the satellite, which is the platform, plus the angular velocity of the wheel times by the inertia of the wheel itself will be my total angular momentum, which is total angular momentum of this system would be angular momentum of the satellite plus angular momentum of the wheel, period. Okay, two components. Now, angular momentum law says this: total of this angular momentum, derivatives of this whole system, the derivatives of the whole system, change of that, what it can change, the external disturbance can change this. That's what it's telling. The Euler's fundamental tells you that. So what I'm going to do, alright, if that is the case, I can't change my inertia. I can't change my inertia of the wheel. When I launch a satellite, my volume is fixed. My inertia is fixed. How can I change this? The only thing I can change is the velocity. In fact, that is what is changing. The satellite velocity is changing. Angular velocity is changing. The wheel angular velocity can change. So I can write this. The platform, the inertia of the satellite remains constant. The angular rate of the satellite can change. When angular rate of the satellite changes, there will be some external, why it changes? Because of some external disturbance, T external. Now, in order for me to nullify that, I need to introduce this wheel. There you go, the wheel comes in here. So the wheel also is going to actually help me. How? It is going to also rotate to counter this external disturbance. Now, when external disturbance torque is equivalent to the actual torque that the wheel produces, this whole term will be zero. When the whole term is zero, the satellite will not actually have any motion. It will be perfectly undisturbed. That is what we are supposed to do. So what he says that, look, whenever you want to counteract any external disturbance to the satellite, please rotate the wheel. Any external disturbance torque, the 4 disturbance torque that we have talked about in chapter 4, disturbing this particular satellite, you want to nullify that, rotate this wheel faster. Then this whole term will be zero. My satellite will be safe. Gone. Okay. My satellite. Okay. I'm back to Euler equation of motion. Euler equation of motion. For example, this is, let's say, it's pitch axis. Okay. You go back. You have a look at it. Euler equation of motion. Pitch axis. You look at the dynamics. This you can assume is a pitch dynamic. Just assume it's a pitch dynamic. Okay. Now, second order equation, S is being Laplace operator. This is basically the inertia of that satellite, I use a PD controller. That means I have a proportional gain and a derivatives gain. KW is my wheel, the reaction wheel that you use. You have disturbance torque. For disturbance torque, you have calculated, will come here. Command, total torque is going to disturb the satellite. I can track back what is the angle, reference angle, I can get back here. So this is the typical scheme of a attitude control system for a satellite with a reaction wheel. Very easy, straightforward. This gives you the actual wheel speed here. So the maximum wheel speed here is going to be what? Let's say I have a 5000 RPM, maybe it goes up to about 4800 RPM. I cannot go higher. So I need to do something. Okay? Now remember this. When you want torque in wheels, you keep on accelerating the wheel. That means the accelerations go higher and higher and higher. So you produce torque up to one end, because the wheel has a maximum speed. Let's say 6000 RPM, 5000 RPM maximum. After that, you can't actually speed this up. So what you have to do, you have to actually bring the speed now to back to maybe nominal. Let's say 1000 RPM or even 200 RPM. You have to bring it back. How to bring back that? That means you should brake the wheel. Brake means what? Slow down the wheel. How to slow down the wheel? You slow down the wheel, you see, if I give a positive disturbance here, then the wheel speed is going to go higher and higher and higher and higher. But if I give a negative disturbance here, the wheel speed is going to be lower and lower and lower. So the only way to slow down the wheel, because the wheel is already maximum speed, slow down the wheel is basically to give a negative disturbance. How to give negative disturbance? I have calculated already 4 disturbances in chapter 4. How to again add another negative disturbances. So which means that I must have some other actuator which is going to actually help me to produce the negative disturbance, which can be added here, so that the wheel speed now will go slower and slower and slower and slower. If your wheel speed, if you go slower and slower and slower, you are also producing torque, but on the other side. That means in the negative side. Okay? You accelerate the wheel, you will have a positive torque. You brake the wheel, decelerate the wheel, you will have a negative torque. Please understand that. So in order to brake the wheel, you must have a torque. So what we can do, we can add another device, and typical device that we know, which is very, very common, we can use magnetotorquers. And magnetotorquers is going to give torque. Let's say B dot. You do a B dot pointing, just give a torque. Keep on adding the torque here. You can actually start giving. Adding means what I'm saying, you have to add a negative torque here for this to break. You add torque here, he cannot respond. If you have a positive torque and this is accelerating, you keep on giving positive torque, this is actually going to go stagnant at maybe 5000 RPM, cannot go further. You can't. Satellite then becomes uncontrollable. Okay? Go on. Okay, now let's see bias momentum principle. Momentum vector is perpendicular to the orbit plane. Okay, I am going to specifically pick bias momentum satellite because why? It's quite typical for a small satellite. If you have a bias momentum principle and with the momentum wheels, in fact with the magnetotorquers, you can achieve quite a reasonable pointing accuracy. In fact, the first Malaysian satellite, Tiong-Sat, that you can I think probably remember, it actually have this principle. So that's the reason quite interesting for you to maybe to know that, so we can discuss this. Momentum vector, basically perpendicular. That means you know that it is on the pitch axis. You must have the wheel, the momentum wheel. Okay, pitch axis continuous control through the change of speed. So if you have momentum wheel, you can have the torque and also the bias momentum. Okay. Roll yaw to improve the passive stabilization, you increase the stiffness. Okay, now this you must understand, when you have the pitch, in a pitch axis you have an angular momentum. just like top spin that I've explained just now. You throw a top spin, spinning very, very fast. It'll be very stiff. You have a gyroscopic stiffness. When you have a gyroscopic stiffness, it actually provides a very good stiffness to other two axes, which is perpendicular to the actual rotating axis. Which are the axes? The roll and the yaw axis are basically going to be quite stiff. Okay, so therefore it actually increases the stiffness of roll and yaw axes by putting the the momentum wheel in pitch axis. But that is all. Okay, it gives you a stiffness to roll and yaw. But don't forget, for pitch axis, it can actually produce active torque when you start actually speeding up the wheel. Okay, go on. Linear equation of motion. Now we have treated a pure Euler equation. Then I mean we have started with the pure Euler equation. Then we have escalated this Euler equation into incorporating gravity gradient component. We have been using that, and we have also treated this Euler equation when we were actually designing the Manitoba Torques control. Now we can use the same Euler equation that we have developed to incorporate another term, which is the angular momentum term. This one. M is being the external torque. M external torque. This is the angular momentum, change of angular momentum, H dot. This is a bias momentum term here. So there's a change of angular momentum. When a change of angular momentum, the wheel speed changes here, that means you have a torque. Okay? So assume this is a minus, this should be plus. Let's say this is plus, this should be minus, so that you try to nullify this so that this particular axis will be stable. Now, remember bias momentum, we are having the wheel on the y axis only. The other two axes are passively controlled. So you have this term H2. It's passively controlled. It's not actively controlled. No active control. No active control. Passive control. Okay? So, how is this called? Again, same convention I use. Roll, pitch, yaw, orbital frequency. We have done this in orbital mechanics. They are the same. The pitch. Okay, pitch bias momentum. Now, again, don't forget, for local vertical, local horizontal, the bias momentum are basically because you are rotating. Should the other way, please? Before this, yeah. When you are rotating this way, for example, okay, when you are rotating, your bias momentum is basically in this direction, the vector. But for local vertical, local horizontal, because your pitch is down, so your bias momentum is basically negative of that. So therefore, go on. Yeah. So therefore, the actual local vertical, local horizontal system, actually it is a 0, 0, negative H transpose. Okay, go on. Alright, simple again, same thing I've treated, roll yaw. Let's see the roll yaw. We don't have to worry much about the pitch, because pitch you have active control. How much of disturbance you give, no problem, because we have momentum wheel. Momentum wheel can give out the torque instantaneously. You can actually start accelerating and give you torque, no problem. Let us worry slightly a bit on the roll and yaw, because it's only passively stabilized by the stiffness. Okay, gyroscopic stiffness. So when we do a analysis, it seems that it produces slightly on a nutation. There is some nutation frequency. Why nutation frequency is there? Because when you produce a stiffness, this is stiff. You might do this. If you throw a top spinning the high speed, you can see it is not like just stiff like that. It may just produce like this. So that means what? The two other angles, that means that the two other axes, roll and yaw, might actually also have a bit of nutation. Okay? So the nutation frequency can be given, can be calculated. Okay? Then uncontrolled roll motion is basically undamped oscillation, you can't do much because there's passive already. Then orbital frequency is actually low, but the nutation frequency is quite high also. So this is something that we need to try to damp this. This is common for bias momentum stabilized satellite. Okay, now bias momentum with 3-axis control. So just now purely bias momentum looks like with the purely bias momentum we can't control 3-axis. Okay, so what we need, I think we need to have maybe bias momentum with 3-axis control. Maybe you have a 2 momentum wheel and maybe 2 reaction wheel. Then you can have a 1 as a redundant. Now, if you see here, I just posted here only 3 wheels. But in the actual, in the mission, if you need to control 3-axis, of course, 2 wheels you can control 3-axis. That's for sure. But just imagine this. Assume that every wheel, every axis, you have 3 axes, every axis needs 1 wheel, let's say. So you have 3 axes. But we cannot fail. Let's say the mission is 10 years, we cannot fail. That means, let's say one of the wheel fail is going to be a catastrophic, almost a catastrophic failure. That means there will be 1 axis uncontrollable. When 1 axis uncontrollable, it's going to be very difficult for us to do mission, high level missions. So normally what we have a redundant wheel. Redundant wheel is mandatory because when there is a wheel failure for a very long missions, 10 years mission, at least 1 wheel is there basically to have it's like a spare tire in the car. Okay, but of course now you do a flat, run flat. But we have that in order for us to have a safe, I would say, safety margin of operation. So you can do, I take this momentum reaction, reaction R wheel. So you have 1 momentum wheel, you have 2 reaction wheel. You can have 2 momentum wheels, you can have 1 reaction wheel. So there is so many combinations actually we can do. Absolutely so many combinations. The list can go on. But the principle is this. In order for you to control 3 axes, you must have, let's say, at least 3 minimum. 3. You must have 2 minimum wheels actually. But let us take it this way. You want to have 3-axis control. Let's say we must have 3 wheels. Then we add another one for redundancy purposes. Done. So you have 4 wheels. Let's say 4 reaction wheels. That's fine. You can actually fly a satellite. Okay, go on. Now we have here another. This is what I talked about. Let's say 3-axis. 0 bias momentum with 3 wheels. That means 3 out of 4. So for example, the satellites that have flown, Rosat, Bird, what they have, just like what I've explained to you, 4 wheels, no bias momentum, all reaction wheel, 4 wheels, and 1 is a backup. And you can control 3 axes with this 3 wheels also. But in fact, the 4 wheels will be actually also operating. Not like 1 wheel will just stand by, not operating. No, you will rotate the wheels. Rotate means like, okay, operation, everyone shares the burden and the 4 will be actually rotated in that sense. Otherwise, you don't use that 1 wheel just like that. It is basically not very effective. You are loading the other 3 wheels. So the distribution, the strategies can vary. Distributions can actually, the top compartment will be distributed evenly. Okay, go on. Now, speed wheel within the predefined, what is that, need. What exactly that you need? Okay, this is something that I've talked about before. Attitude controller, you have the momentum wheel. This is basically, it gives you, this is the block diagram that I have explained just now on the wheel, same, but this is simplified. Then you have the satellite, 1 over JS S squared. This is the plan. Then you have the attitude. Okay, maybe go back to the reaction wheel. Yes, go. Control block. This is the same one. This part. Take this part. Page 13. Let's insert there. We insert here. Same. Okay. Close loop. Only difference here is this. Remember, I told you the problem of the wheel is speed is actually going maximum. So what I add here, I add an actuator. And I call it a momentum management, momentum of the wheels. To manage it, I have an actuator. And what actuator normally I use to manage this is basically our torques. So this will, you see, it acts just like an external disturbance. Positive torque, this gives you negative torque. Negative torque, the wheel will slow down because it produces negative torque. You accelerate, you have positive torque. Decelerate, you have a negative torque. Okay, what? Again, this another options, you can always use thrusters, but expensive. Best use magneto torques. Thrusters keep for orbit control. You can live longer. For satellite, especially gone. Okay, now I have combined all those actuators that you have learned here. Gravity gradient, boom. More important here in this whole diagram here is to look and observe the axes that I have picked to install the exact device. Look at my boom, your axis. Okay, there are also some satellites. Boom is going to be here. Also, there are. There are. So, by here, basically, especially like for example, there's some camera, there's some antenna also sometimes. Some antenna is here, camera is here. So, depends. But here, I said this is very, I would say, common design. Gravity gradient boom along y-axis. Momentum wheel. I have momentum wheel, that means what? My pitch axis is done. Pitch axis, I have a active control already. Then I can provide a passive control or rather gyroscopic stiffness for roll and yaw. The pitch axis can produce roll and yaw passive stiffness. Okay, done. In order for me to, let us see, now I must control my pitch, my roll and yaw control. I must do this. So what I do, I install a magneto torques along the pitch. We have learned in Thomson control, you install a pitch torques, you will have yaw and roll control. Yaw and roll control. Done. Why I need? Because I can only, the momentum wheel can only provide you a passive control. That means the gyroscopic stiffness only. That means the nutation is still high. It will nutate. Remember, it will just nutate. So in order to dampen that, you provide this. Don't forget, another problem that we have, momentum wheel will start actually building the speed. So what I need to do, I need to break this wheel. I need to have another torque which takes care of that wheel momentum. Yeah. This is a complete satellite which gives you a solution of using all those devices that I've introduced to you. Complete. Okay? Complete. You have all those fundamentals. You have passive stabilization, gravitational passive stabilization. You have a very cheap way of a low cost way of controlling the satellite, magnetic torques. You have a very good pointing capabilities by having a momentum wheel itself. Right? Got. Okay, looking at the performance here. Look how beautiful this performance. You can get 0.5 degrees. That's very good compared to just now. Remember, there was an extreme case. Of course, you can see in some of the literature or some of the satellite applications that with the X, Y, Z Thomson pointing, we can still achieve a reasonable pointing accuracy. Probably about 10 degrees. Yeah, 10, 15, 10 degrees. I think it is beyond about 5 to 10 degrees. We can still achieve that, but not 0.5. yeah, not 0.5. If you can, the X, Y, Z, let's say Manitowoc Thomson pointing, let's say Thomson solutions that we have, we can optimize, keep on optimize. Probably we can do maybe 5 to 8 degrees, 10 degrees, but it's very difficult. It's not easy. We can actually roll and yaw is 0.5. Okay, now it is just the same. Your external disturbance I have 4 already, just like you have calculated in chapter 4. Will bias momentum. This satellite that you see, it's about 50 degrees, 50 kilograms. It's about 50 kilograms, and I think it's about 53 degrees of altitude. So those are the performance, the typical ones that you have. Okay, go on. Now, I want, before this please, why I didn't actually show the pitch. Why I didn't show the pitch performance? Because the pitch performance, I can achieve with the momentum wheel. Let's say the accuracy of momentum wheel is 0.01 degree. I can reach 0.01 degree in pitch. No problem. It's not a problem. But with 0.5 degrees, I'm all the time. It's enough for me. It's enough to actually run a very, very good mission. Yeah. Okay, one. Okay, a bias momentum pitch and pitch basically calls. So I have basically the bias, and is stored there, highly sufficient, about 6 Newton meter second. In some exercises that you see that in last chapter, chapter 5, where you have that all those magnetic torques, you have also seen I have example of 8 Newton meter second of bias momentum. Yeah, you have that. It's an open loop dynamic. Remember the B dot pointing of Manitowoc? That is an open loop. But this is actually, sorry, that is an open loop. Open loop pointing here is basically your the pitch motion, which is decoupled through the bias momentum. That means what? Your roll and motion is basically coupled, and your pitch is actually giving a passive stabilization to the roll and your axis. That means gyroscopic stiffness. Okay? Mutation, just like we have calculated just now, it's quite high effect. So therefore, what we need to do, we need to actually give a pitch control. Pitch control is really perfect. No problem. We don't have to talk about the pitch control because it's perfect. You look at the if you want to buy a reaction wheel, the reaction wheel will manufacturer will specify this is going to give me an accuracy of, let's say, 0.001 degree. So minute. So that's the accuracy that you have in the pitch. Okay. Wheel unloading, basically we can do Manitowoc, roll and yaw. Our magnetic torques, we have also proven that our magnetic torques can dampen that. The only problem that we have, at any time it is only possible to generate 2 axis torque, because there's always, that is the issue with that, because you can never get that the magnetic field, planet Earth's magnetic field, perpendicular to all the 3 axes. No, you can get it perpendicular to 2 axes in order for you to find the torque, but not all 3 axes. Okay. No perfect control is possible. But again, don't forget, roll and yaw 0.5 degrees with very sort of a low cost control options that you have. You can still actually have a 0.5 degrees of accuracy, which is reasonably well. Okay, the backup mode. Backup mode says that wheel is deactivated, means the wheel is dead. There is no redundancy here. Wheel is dead. So the wheel is dead. Open loop dynamics again will be decoupled. Pitch motion is decoupled, is undamped, and this go back to your again gravity gradient mode. We have covered this in chapter 4. Again, go back to gravity gradient stabilization. Damping is possible through magnetic torques, steel dot, but the problem is that again you can have only two to axes at one time. Now look at the actual problem here. Components, the components basically of the pitch, just because there's no perfect control. Now you can actually look at the order of accuracy you will arrive, 1 to 10 degrees. This is what I will telling you. So even the best control, best way I want to dampen using the magnetotorcus, well, for 5 to 10 degrees to be safe, to say, not better than that. So which means, and you can see how much of differences that one momentum bias will have made to the whole system. The pointing is 0.5 roll and yaw. The pointing at basically pitch can be also perfect. Yeah? I think more or less. And is that? Yeah. So thank you, and we'll continue.